Let us see about metal semiconductor junction, that is Mesfet, Finfet, Pinfet and Cntfet. Let us see about the metal semiconductor junctions. That is, the metal semiconductor junctions are very common in all semiconductor device and has also very high importance. Here it is depending upon the doping concentration materials and depending upon the doping concentration materials and the characteristics of the interface, the metal semiconductor junction acts as either an ohmic contact or a Schottky barrier. Here, the metal semiconductor junction consists of a metal in contact with a piece of semiconductor, and the structure of the typical metal semiconductor junction is shown. And here the active junction is the interface between the metal which acts as an anode and the semiconductor. The other interference between the semiconductor and metal which acts as a cathode is an ohmic contact, and there is no potential drop at this point. While we are seeing this energy band diagram, it helps in identifying the barrier between the metal and the semiconductor. In order to understand the energy band structure at a metal semiconductor junction, first let us consider the energy band in metal and semiconductor separately. The energy band are aligned at the same vacuum level, and here when the metal and the semiconductor are brought together, the Fermi level doesn't align them at thermal equilibrium. Here let us consider phi b, that is the barrier height, as the potential difference between the Fermi level of the metal and the band energy via the carriers via the majority carriers exist. Here for an n-type semiconductor, the barrier height ID given by the difference between the metal work function and the electron affinity, that is phi bn equal to phi m minus x. And also here when we are seeing here that is the work function phi m varies depending upon the surface separation. For p-type semiconductor, the barrier height is given by the difference between the valence band and the Fermi level in the metal. And also here phi bb equal to x plus, it is given by the same given equation, and Eg is the energy gap between the conduction and the valence band. And sum of the barrier heights on n-type and p-type structures are expected to be equal to the energy gap. Therefore it is given by this equation. And here for the n-type semiconductor, the barrier height is given by the equation, that is phi bn equal to phi m minus x, and while we are substituting the values, we are getting this equation. Here the p-type semiconductor, the Fermi level is closer to the valence band, and the built-in potential is given by phi p equal to, this is given by this equation, and the Fermi level in the n-type semiconductor is given by this equation, and the Fermi level in the p-type semiconductor is given by EPF equal to EV plus KT into ln of NV by NA. And substituting the above equation, we are getting the Fermi level for n-type, and this is for p-type semiconductor field effect transistor. While we are seeing for this metal semiconductor field effect transistor, it states for metal semiconductor field effect transistor. Here it is quite similar to the Cntfet in construction and term technology, and the difference is the instead of by using the PN junction of a gate, a Schottky junction is used. The Mesfets are usually constructed in common semiconductor technologies lagging high quality surface passivation such as gallium arsenide, INP or SiC, and are faster but more expensive than silicon based Cntfet or MOSFETs. And the production Mesfets are operated by up to approximately 45 GHz and are commonly used for microwave frequency communication on radar. From a digital circuit design, it is increasingly difficult to use Mesfets as the basis for digital integrated circuits as the scale of integration goes on compared to CMOS silicon based fabrication. The metal semiconductor field effect transistor consists of a conducting channel position between the source and the drain contact region, and here the carrier flow from source to drain, and it is controlled by a Schottky metal gate. and the channel is obtained by varying the depletion layer with underneath the metal contact, which makes the thickness of the conducting channel and thereby the current between the source and the drain. Here this shows the Mesfet characteristics. Next one is the pin diode. While we are seeing this pin diode, here the pin diode stands for p-type intrinsic and n-type field effect transistor, and here it is an integration of pin photodiode and FET in a single IC. Pin diode converts light energy into an electrical signal, and it is designed to operate in a reverse bias condition. Field effect transistor, it is a voltage control device. The voltage which is given in the gate terminal as input controls the current passing through it. This is the construction of pin diode. While we are seeing the construction, it is the combination of gallium arsenide pin diode and indium gallium arsenide FET. The construction it includes the metal organic chemical vapor decomposition. By using the method, Pinfet is fabricated over semi-insulating INGAS substrate, and the chloride vapor phase epitaxy by the process of INGAS layer of low concentration of electrons is grown above the substrate. And third one is atmospheric pressure and metal organic chemical vapor decomposition technique. And next one is ion implementation. By this process, which is done in series, the FET is found, and the decomposition and deposition by this process pin diode is formed. While we are seeing the working of pin diode, here Pinfet, it consists of 3 layers of P region, I region and N region. P region and N region are heavily doped regions, and they are used as ohmic contacts. A wider intrinsic silicon layer is sandwiched between two heavily doped layers, and is absorbs the light photons, which forms the electron hole pairs, and the intrinsic semiconductor and the intrinsic layer is highly resistive, and it increases the width of the depletion region. In normal diode, only voltage is used to form the current, but in Pinfet, both voltages and light is used to form the current. When reverse bias, the majority carriers is heavily doped p-type and n-type and does not conduct current. So the charge carriers move away from the junction, and the intrinsic layers is doped, which does not have majority charge carriers. So the width of the depletion region increases when the light is incident on the pin diode. The width in the intrinsic layer absorbs the light energy and forms larger number of electron hole pairs. The free electrons which are generated in the intrinsic region moves towards the N region, and the free holes move towards the p-type, and this charge carriers are attracted towards the positive and negative terminal, and this current is formed due to the movement of these 3 charge carriers. And the intrinsic layer acts as a dielectric layer, and the highly doped p and n layer acts as the electrons in the capacitor. Since the distance between the electrons are very large and the capacitance very low, and then the noise is very low. That's all about the working of pin diode. Thank you.